Hi friends, today I am going to explain what is meant by forward bias and reverse bias in the PN junction diode. So in the last class we discussed about what is meant by p-type material, p-type semiconductors, or what is meant by n-type semiconductors, and how that PN junction is formed. So if you are not yet watched the video, I will put the link in the description. You just go and watch. So first, in the case of PN junction, so this is my p-type material, this is my n-type material. In the case of p-type material, we have a holes are the majority carriers. In the case of n-type material, we have the electrons are the majority carriers. So there is a flow of electron from n to p type, p side, and there is a flow of holes from p to n side because of the concentration gradient. So whenever the electron moves from n to p, it leaves a positive ion here. Whenever the holes is moving from here to here, it leaves a negative ion here near the surface of the n side and near the surface of the p side. So there will be a formation of the depletion region. Once the system attains a barrier potential, so I can simply write, so this is called your barrier potential is said to be V naught. Once the system attains barrier potential, there is no further flow of electron from n to p and holes from p to n. Sir, once the system attains equilibrium, there is no flow of electrons. Then how can we overcome this problem? So we are going to give some external voltage potential. So external potential, it's called biasing. So if I connect my positive terminal of the battery to the p side, then it's called forward bias. Then it's called forward bias. So positive side of the battery is connected to the p side. It's called forward bias. Forward bias. Sir, what's happening? So there will be already a potential, it's called your stopping potential. It's a potential difference between your p9 n-type material. So it's a potential difference between the PN junction. So this my applied potential is called V. Sir, once the system attains the barrier potential, there is no flow of electrons from n to p and holes from p to n. Sir, what's happening? Here, this positive charge which will attract my electrons from this side to this side, because this is my positive charge which will overcome my barrier potential, which will attract my electron from here to here. And then what's happening? This negative charge which will attract my holes from p side to n side. So because of this applied external potential, my barrier potential will reduced. So I can simply write, so this is my barrier potential is V naught. If I say this my barrier potential is V naught, my applied potential which will reduce my barrier potential, which will increase the number of electrons from motion of electron from n to p, and which increase the motion of holes from p to n. So my applied external potential which will reduce my barrier potential. So because of the applied external potential, there is a flow of electrons and flow of holes from either side. So because of this, what's happening? Because of some current will flow. So this is the happening because of the majority carriers. So this is the flow because of the majority carriers. So I can simply write the logical diagram here. So this is my PN junction diode. Okay. So I am going to connect this with a positive terminal, and I am going to connect a ammeter here. This is my milliammeter. For forward bias is going to be milliammeter. Okay. So I just want to measure the potential. If you want to measure the potential here, I am going to use a voltmeter here. Okay. So which is parallel to this, which is parallel to this. So then I can find the potential drop across the PN junction. So my applied potential which will reduce the barrier potential. Because of that, there is a flow of your charge carriers. So listen here, I am able to find the applied potential here or the potential difference between the PN junction and the current from here. So if I plot a graph between these two parameters, then I can simply write, so we have a applied potential V versus the current I. This is in milliampere. Sir, even though it's an extrinsic semiconductors, it's a PN junction formed, so we have to provide some small amount of energy to the system. So till 0.6 or 0.7 volt, there is no increase in my current. If I increase my voltage, there is no increase in my current. After 0.6 or 0.7 volt, the current will increase drastically. So because of this applied potential, the current will increase. I can measure the reading from here. This is the order of milliampere, 10 power minus 3 amperes. So there is an increase in the current. Sir, if there is increase in the current, because applied the small potential. So after that, what's happening? We need not to apply any potential. The electrons, the charge carriers moving from either side, which will increase my current drastically. So if under forward bias, my PN junction conduct current very drastically, right? So if I take the slope of this curve, this is my VI characteristic curve of the PN junction diode under forward bias. If I take the slope of this curve, so if I take the slope of this curve, I can get a change in current and change in potential. So from the change in potential and change in current, I can calculate the resistance. It's called dynamic resistance. This is very, very important for the numericals. So I'm going to define a new quantity called your dynamic resistance. So it's called dynamic resistance. So why it is called dynamic resistance? Because for small applied potential, there is a drastic increase in the current. The electrons and holes moving from either side very drastically. So that's why it's called dynamic resistance. So I can simply write R small d or subscript d. I can simply write change in potential by change in current. V is equal to IR, R is equal to V by I. So from this slope, I can find the resistance. It's called dynamic resistance. Sir, what's happening when I reverse the polarity of the applied potential? We are going to study in the next case. So this is the current produced by the motion of the majority carriers. So under forward bias, the electrons will, under forward bias, the PN junction diode will conduct drastically. Right? Next, I am going to change the polarity. Because of the change in polarity, how that barrier potential will change? Because of the change in barrier potential, only decides the amount of flow of electron from one point to another point. Okay. Next, we are going to discuss about the reverse bias. So what I am going to do here, this is my applied barrier potential. So I am going to reverse this, right? So I am going to use the same diagram here. Here also I am going to use the same diagram. Okay, for the reverse bias, so reverse bias I am using a high potential, no problem, it's my applied potential V. Okay, so here also I am using a potential V. Here this is my positive terminal, this is my negative terminal. So I have to reverse this, sorry. Positive, this is negative. So if I connect the negative side to P, it's called reverse bias. P side positive means forward bias, P side negative means reverse bias. So in this case, P side is negative, then it's called reverse bias. So I'm just reversing the bias. Sir, because of the reverse bias, how my barrier potential will affect? Will change. Listen, this positive charge which will attract all the electrons from here, already because of the barrier potential, there is no flow of electron from N to P and hole from P to N. Because of this applied external potential, the electrons attracted by this positive terminal and the holes in the majority carriers is attracted by this negative terminal. Even because of this, what's happening? There is no flow of electron because the electrons are attracted by this positive terminal, which means the barrier potential will get increases. So my applied external potential, which will increase my barrier potential, V naught plus V. So already there is a barrier potential. Because of the barrier potential, there is no flow of electron and hole from either side. Your applied potential, which will increase my barrier potential. Because of this, there is no further flow of electron from N to P and holes from P to N. Because of the number of electrons leaving from here, it leaves a large number of positive charges, positive ions, and here it left a large number of negative ions here. Because of, not only because of that, this positive charge which will repel my holes from here to here, this negative charge which will repel my holes from here to here. So because of this, what's happening? The width of the depletion region which increases. So this is called W. The width of the depletion region gets increases. Because of the width of the depletion gets increases, which will increase my barrier potential. So there is no flow of electron from N to P and holes from P to N. So if I plot a graph for, I'm measuring my potential and current here. So in the case of reverse bias, we have a ammeter is called microammeter, 10 to the power minus 6. Okay, microammeter. So if I increase my potential here, there is no increase in the current. I'm varying my potential, my applied potential, which will increase my barrier potential. Because of the increase in the barrier potential, there is no current will flow. If I increase this, nothing will happening. So from this experiment, I am coming to the conclusion, my PN junction under reverse bias won't conduct. Okay, my PN junction under reverse bias which will not conduct. The forward bias for applied for the very small potential, there's a drastic increase in current because of the applied external potential, which will reduce my barrier potential. In this case, because of this applied potential, which will increase my barrier potential, because of the increase in the barrier potential, there is no increase in my current. So I'm coming to the conclusion, under reverse bias, PN junction won't conduct. Sir, this is what happening. Then how can I use the system? Simple logic. I'm going to increase my potential further. If I increase my potential further, what's happening? The barrier potential gets break down. The barrier potential gets break down. Once the barrier potential gets break down, what's happening here? My minority carriers plays a role. Here we have minority carriers of electrons. So these two are majority carriers. Here electron is a minority carriers. Here hole is the minority carrier. Because of the minority carriers, what's happening? The electrons is attracted by this positive terminal. Actually, before that, what's happening? These negative charges which will repel my electron, these positive charges which will repel these holes to move from here to here. What's happening? Because of the strong applied potential. That's why I use instead of a cell, I'm using a strong high tension battery. Okay, so if I increase my potential further, what's happening? The electrons is attracted by this positive terminal, it moves from here to here. My holes attracted by this negative terminal, which will overcome the repulsion produced by the positive charge. Then the electron is moving from here to here. The holes are moving from here to here. So once the depletion region is break down, once the PN junction is break down, there is a flow of minority carriers, the electron from P to N and holes from N to P because of the applied external potential. So then there is a drastic increase in the current. So this potential is called the breakdown potential or breakdown voltage. This is very, very important concept. Okay, so based on this principle, voltage stabilizers working. Okay, so it is called, sometimes it's called Zener voltage. So this kind of diode was called Zener diode. So again, those things we will discuss in the next class. So whatever the increase in my potential, there is no change in my current, there is no increase in my current. So under reverse bias, PN junction won't conduct. Once a breakdown is happening, there's a drastic increase in the current, but in the order of 10 power minus 6 because of the motion of the minority carriers. This is because of the motion of the majority carriers. Because the forward bias because of the motion of the majority carriers, the reverse bias because of the motion of the minority carriers is not happening initially. Once the system attains breakdown, then only it will happening. Why it's not initially conducting? Because my applied potential which will increase my barrier potential. So this is very important concept. So listen carefully. What we people thinking, at a particular potential there is a drastic change in my current. This is what we are thinking. But the Zenner is a scientist. He is thinking differently. Whatever the change in current, my applied potential is same. So this kind of special function diode, it's called Zener diode. This is also same PN junction diode, but it's heavily doped. It's called Zener diode. So those diodes we are using in the stabilizers, to voltage stabilizers. Whatever the input current, your output potential should be a constant. Okay, those things we will discuss in the next class. So in the next class, what we are going to discuss here, so using this property, this PN junction under forward bias conducts, PN junction under reverse bias won't conduct. Using this property, we are going to construct a rectifier. It's called half wave and full wave rectifiers. What is meant by rectifiers? To convert from AC to DC, alternating current to direct current. So those things we will discuss in the next class. So I just stop at these points. If you like this video, share with your friends and subscribe our channel for the more content. And we have a separate playlist for the practicals. You can just go and check it out. Thanks for watching. We'll meet in the next class. Thank you.